Ever wonder why ships float while stones sink? Or how airplanes stay in the sky? The answer lies in a fascinating field of physics that affects everything from your morning coffee to massive oil tankers. Hey there, today we're diving deep into the world of fluid mechanics, the science that explains how liquids and gases behave and why understanding it matters in our everyday lives. By the end of this video, you'll see fluid mechanics at work everywhere around you. And I'll show you how engineers use these principles to design everything from dam systems to airplanes. Let's get started. Fluid mechanics is the branch of physics that studies fluids, liquids, and gases, and the forces acting on them. Unlike solids, fluids can flow and change shape when forces are applied to them. This unique property is what makes fluid mechanics so interesting and complex. The science of fluid mechanics can be broken down into two major areas: fluid statics, studying fluids at rest; fluid dynamics, studying fluids in motion. When we talk about fluids at rest, we often use specific terms: hydrostatics when dealing with liquids at rest, aerostatics when dealing with gases at rest. One of the fundamental principles in fluid mechanics is that in a fluid at rest, there's no relative motion between adjacent fluid layers. This means there are no shear stresses trying to deform the fluid. The only stress we need to consider is normal stress, which we call pressure. And the variation in pressure is primarily due to the weight of the fluid itself. Pressure is defined as the normal force exerted by a fluid per unit area. The standard unit for pressure is Pascal, PA, which equals 1 Newton per square meter, Ns per meter². However, since a Pascal is quite small for practical applications, we often use kilopascal, kPa equals 1000 PA, megapascal, M1000 PA. In many countries, particularly in Europe, you'll also encounter bar, 1 bar or equals standard atmosphere in 1,325 PA, kilogram force per square centimeter, 1 meter square equals 98,066.5 PA. In the English system, pressure is commonly measured in pounds force per square inch, psi, where 1 atmosphere equals 14.696 psi. When we measure pressure, we need to understand three important types. 1. Absolute pressure, measured relative to absolute vacuum, zero pressure. 2. Gauge pressure, the difference between absolute pressure and local atmospheric pressure. 3. Vacuum pressure, pressures below atmospheric pressure. These are related by a simple equation. Pabsolute equals P gauge plus patmospheric. For vacuum pressure, P vacuum equals patmospheric pabsolute. Here's something fascinating about pressure in fluids. It acts equally in all directions at any given point. This means pressure is a scalar quantity, not a vector. It has magnitude but no specific direction. This property leads to one of the most important principles in fluid mechanics, discovered by the French scientist Blaise Pascal. Pascal's law states that pressure applied to a confined fluid is transmitted throughout the fluid and acts equally in all directions. This principle is what makes hydraulic systems work, from car brakes to heavy machinery. In a fluid at rest, pressure increases with depth due to the weight of the fluid above. For a fluid with constant density, the pressure difference between 2 points is del P equals G Z2 minus Z1, where d is the fluid density, G is the gravitational acceleration, Z2 minus Z1 is the vertical distance between the points. This means pressure in a fluid increases linearly with depth, regardless of the container's shape or cross-section. This is why the pressure at the bottom of a tall, narrow tube of water is the same as at the bottom of a wide lake at the same depth. It only depends on the vertical distance. How do we actually measure these pressures? Several devices have been developed. Manometers. One of the simplest pressure measuring devices is the manometer, a U-shaped tube containing a liquid, often mercury or water. The pressure difference is proportional to the height difference between the two sides of the liquid column. The basic equation for a simple manometer is P1 minus P2 equals 3GH, where H is the height difference between the liquid columns. Barometers. A barometer is specifically designed to measure atmospheric pressure. The classic mercury barometer consists of an inverted tube filled with mercury in a container open to the atmosphere. The height of the mercury column is proportional to the atmospheric pressure. Standard atmospheric pressure can support a mercury column of 760 millimeters at 0 degrees Celsius, which is why we sometimes express pressure as mmHg or torr. Mechanical pressure gauges. The Borden tube gauge is a common mechanical pressure measuring device. It consists of a curved tube that straightens when pressure is applied, moving a needle on a calibrated scale. Pressure transducers. Modern technology has given us pressure transducers that convert pressure into electrical signals. These can be more precise, responsive, and versatile than mechanical gauges. Hydrostatic forces. When fluids push back. When a fluid is in contact with a surface, it exerts hydrostatic forces. For a flat surface submerged in a fluid, the total force is F equals PA, where F is the total force, P is the average pressure at the centroid of the surface, A is the surface area. For a vertical rectangular plate of height B and width A with its top edge at distance S below the surface, F equals GS plus B2 AB. The force acts at a point called the center of pressure, which is generally below the centroid of the surface where the pressure is higher. Have you ever wondered why some objects float while others sink? This brings us to one of the most fascinating aspects of fluid mechanics: buoyancy. When an object is immersed in a fluid, it experiences an upward force equal to the weight of the fluid it displaces. This is Archimedes' principle, and it explains why large steel ships can float despite being made of a material denser than water. For a completely submerged object, the buoyant force is Fb equals the fluid g of object. For a floating object, the weight of the object equals the buoyant force, which equals the weight of the displaced fluid. Object equals Fb equals the fluid and gv submerged. This means the fraction of a floating object that's submerged equals the ratio of the object's density to the fluid's density. V total equals the object fluid. The challenge of stability. Let's consider a practical problem that engineers face: ensuring stability of floating vessels. Imagine a large ship carrying cargo. As waves hit the ship, it tends to roll from side to side. If the ship rolls too far, it could capsize, a disastrous outcome. How do engineers ensure this doesn't happen? The answer lies in understanding the metacentric height, the distance between the center of gravity and a point called the metacenter. For stability, the metacenter must be above the center of gravity. When a floating body tilts, the shape of the submerged portion changes, moving the center of buoyancy. If this creates a restoring moment, a rotational force that returns the body to its original position, the vessel is stable. If it creates an overturning moment, the vessel is unstable and will capsize. This is why ships have ballast tanks below the waterline. They lower the center of gravity to increase stability. Cruise ships and tall vessels face particular challenges in maintaining stability while providing comfortable upper decks for passengers. Fluids in motion. So far, we've focused on fluids at rest, but what happens when fluids are accelerated? When a fluid container accelerates, interesting phenomena occur. For example, in an accelerating tanker truck carrying liquid, the free surface of the liquid tilts, with the fluid rising at one end and dropping at the other. The angle of this tilt depends on the acceleration. For a container accelerating horizontally with acceleration A, the slope of the free surface is slope equals Nias A war G. This explains why your coffee tilts in the cup when you accelerate your car. Even more interesting effects occur when fluids rotate. When a cylindrical container of fluid rotates about its vertical axis, the fluid's free surface forms a parabola. This is why stirred liquids form a vortex with a depression in the center. Applications of fluid mechanics. Fluid mechanics principles are applied in countless ways in our world. Engineering applications, dam and reservoir design, hydraulic machinery, elevators, brakes, industrial equipment, ship and submarine design, aircraft aerodynamics, ventilation and air conditioning, systems, pipe networks for water distribution, natural phenomena, weather patterns and atmospheric pressure systems, ocean currents, blood flow in the human body, groundwater movement, industrial applications, oil and gas extraction and transportation, chemical processing, food processing, power generation, hydroelectric, wind turbines. One fascinating application is in the design of hydroelectric dams. Engineers must understand hydrostatic forces to ensure the dam can withstand the enormous pressure exerted by the reservoir. They also use fluid dynamics principles to design efficient turbines that convert the water's energy into electricity. Another important application is in aircraft design. Understanding how air flows around wings creates lift is crucial for aviation. The same principles explain why race cars use inverted wings to increase downforce for better traction. The future of fluid mechanics. As our understanding of fluid mechanics advances, new applications continue to emerge. Microfluidics for medical diagnostics and drug delivery, improved weather and climate modeling, more efficient renewable energy systems, advanced water purification and desalination, reduced drag in transportation to save energy. These advancements could help solve some of our most pressing challenges, from clean water access to climate change mitigation. Conclusion. Fluid mechanics may seem like a complex theoretical field, but it's incredibly practical and present in our everyday lives. From understanding why ships float to designing efficient water systems, the principles we've explored today impact virtually every aspect of modern life. The next time you see waves crashing on a beach, watch an airplane soar overhead, or even just pour a glass of water, remember the fascinating science of fluid mechanics at work. It's a field that connects physics, engineering, and the natural world in beautiful ways. Did you find fluid mechanics as fascinating as I do? If you enjoyed this video, check out our next one on aerodynamics, where we'll take a deeper look at how aircraft actually fly. Click the video on your screen now.